Today we're going to do section 1.3, and I think that you will like this section. This section is going to feel more algebraic than anything we've done so far. The title is Evaluating Limits Analytically. When you see the word analytically, it's interchangeable with the word algebraically. Okay? So write that down somewhere. Analytically equals algebraically. And I will tell you that I use them interchangeably. So if you see something in a quiz question or a test question that says analytically, you should know it means algebraically. Or if it says algebraically, you should know it means analytically. However you're thinking about it, they mean the same thing. So for starters, we're going to take a look at some basic limits. We've done limits two different ways so far. Numerically, that's the table. That was quiz question 3. And graphically, that was quiz question 2. Now we're going to do them with some algebra analytically. So some basic limits, that we're going to take a look at. So B and C are real numbers, and N is a positive integer. If you have the limit as x approaches C of a constant B, then the limit is B. I'm not going to justify every single one of these, but some of them are really easy to see why they make sense. This one right here is one of those. This right here, is just an equation y equals some number. That is not a hashtag, that's a number symbol. And y equals a number means it's a line that's horizontal. So clearly, everywhere along a horizontal line, whatever that value is, this one's called B, it's the value B. So no matter where you are, you're getting close to it. In fact, you are on the y value of B. Okay? So if you have a constant, its limit is itself. The second one, if you have the limit of x as x approaches C, then the value is C. This one's also pretty easy to see why it makes sense. So having x means that you have an equation, y equals x. And the graph of y equals x is this line. Everywhere along the line, x and y are the same thing. So underneath the limit notation, right, on number 2, it says x approaches C. So clearly if x is getting close to C, y is getting close to C because the equation is y equal x. Number 3 kind of feels like a continuation of that. And what it really looks like we're starting to do, if you look at 2 and then you look at 3 in succession, is that we're just taking x and we're replacing it with C. Do you see that? X is C, and then the x is C. X is C, and then x is C. Do you see all how there, it looks like there's a replacement? That is really what's happening, actually. When you have what I'll call nice functions, and I'm going to leave that a little ambiguous for the moment. When you have nice functions, you really can just take x out and put the number in that they're telling you x is getting close to. And the problem is not all of our functions are going to be nice. So let's keep working with the nice ones for a moment, okay? So some properties of limits. Limits are actually really nice because they do everything you would expect them to do. B and C are real numbers just like before. N's a positive integer just like before. F and G are functions that have limits. It tells us that the limit of f of x is L and the limit of g of x is k. Okay, so there's some number, whatever they are, they're L and k. The first one is scalar multiple. It says that if you have some number b multiplied by f of x, in a very real sense, you can pull this b out in front. Everything you're left with is limit of f of x, looks just like this. And that b will get multiplied by the limit value L. The second one, sums or differences, say that if you have addition or subtraction of these functions, you can just add and subtract their limits. It's exactly what you would expect. 3 is the product. If you multiply f of x and g of x and take their limit, it's the same thing as multiplying their limits. Everything that seems like it's intuitively going to or should maybe happen works with limits. They're very friendly to our intuition. There's a couple more, but I'll wait till you guys are finished writing those in. Okay, so we've got scalar multiple, sums and differences, product. There's two more. Quotient is next. The quotient says that if I divide the two functions and take their limit, it's the same thing as taking the division or the quotient of the limit values themselves, L and K, as long as K is not 0. And generally speaking, K could be 0, but in this context it couldn't because I would end up creating a 0 in the denominator. This creating of zeros in the denominator is going to be, in particular, the kinds of functions that are going to be the not nice ones I'm talking about, and we'll have to approach them in a slightly different way. And then number 5 is powers. And what it basically says is that if we have a function, f of x, and it's raised to a power, and then we take the limit, we could actually find the limit first and then raise it to a power. We can interchange those kind of operations. It's almost an extension of the basic. I'll come back to this slide. This basic one, number 3 here, right? Where there's a power over there. It's just that there's not an x in it. It's an f of x function. So it's kind of an extension of that one. Okay, so all of this theorem, theorem 1.2, looks really formal. It's got a lot of notation in it, but I keep telling you it's very intuitive. So I'm going to do the next problem in 2 different ways. I'm going to show you how the limits are being used from a very formal perspective, like why it's all working. And then I'm going to show you what you sort of get to be able to do, not exactly for free, but because of the formal stuff working intuitively. Okay, so I'm going to show you all of it with these details and this stuff, and then I'm going to show you how you can actually work with it because it works so nicely. So here's our first example. If the limit as x approaches 1 of negative x squared plus 1. And what I'm going to do first is show you all the details that match up with what we did before on the previous theorem. So what the previous theorem says I can do is that I can separate this because it's addition into 2 limits. It's the limit as x approaches 1 of negative x squared plus the limit as x approaches 1 of 1. Okay, it says sums and differences, I can split them up. And then it says, hey, so there's a negative in front of the limit of x squared. That's a constant multiplier. It's a scalar. That's property number 1. I can put that negative in front of the limit and write it there instead. So I'll write this as a negative 1 out here. And then I'm going to rewrite this. Limit as x approaches 1 of x squared plus the limit as x approaches 1 of 1. And then I notice, hey, look, x is squared, right? That's a power. So that's property, what we said, I think it was number 5, right? If I have x squared, it's actually basic property number 3 as well from the previous theorem. I could actually rewrite this so that I take the limit as x approaches 1 of x first, and then square it, and then add the limit of 1 as x approaches 1. This is what all those theorems say I'm able to do. I'm able to separate it in all of these ways. And then at this point, I can actually use basic limits. So this one that's in the brackets, flip back to the basic limits on the front of your handout. What does it say I can do with the 1? Yeah, the limit is 1. It says that when I have an expression like this where it's just x, it just becomes the value that the x value is approaching. So this piece right here is 1. So I end up with -1 out here. I end up with a 1 squared here. And then I end up at the end with the limit of 1. That's another one of my basic properties. It's the very first one. When I have a constant, it's just the constant value 1. So this is 1. So now I have a negative times 1 squared. 1 squared is 1 times the -1 is -1 plus my 1, and my result is 0. Okay. That's the why it works. That's all of the stuff that's going on behind the scenes, all written out in a very formal way. I don't need you to write it out in a very formal way, but I wanted you to see one so you can see that it's really working behind the scenes. Here's what you can actually do with this problem. So this is all of the hard, like behind the scenes stuff. Because it all works out the way we expect and that we want, all we have to do is to take the number that x approaches and substitute it in. This says negative. I replace the 1 with the x with 1 and plus 1. Okay, 1 squared is 1 times the -1 gives me -1 plus 1 is 0. And you can see what it is it's the last part of what I did before. So I don't show you that to make you feel like, well, why'd you go doing it the hard way? But there is a reason behind why it works. It's not just that we get it for free. It's just that it's working intuitively the way we would expect it to and hope that it would. So if I were to write out this next one, number 2, the same way, I'd have a quotient. And I'd have scalar multiples, and I'd have sums and differences, and it'd be really long and messy. But we don't have to write it all out like that, because everything we wish and want to be true is going to work, which means that I attempt anyway to take the -3 and plug it in. And it will work on this one. We'll find one soon that it won't, but here it does. So the -3 replaces the x. And we simplify with basic algebra 1 stuff. Okay? 2 times -3 is? -6 minus 3 is -9. On bottom, -3 plus 5 is +2. You can leave it written like that. You can change it if this bothers you. You don't like things written as most math people really like improper fractions, just so you know. I'm very much a fan of improper fractions. But if you don't like them, you can change it, in this case, into a decimal. It works just fine. If it's a repeating decimal, don't do that. That's definitely not a very nice way of writing it mathematically. But here it works out nicely. Or if you wanted to write it as a mixed number, which is probably our least favorite in the math world, and the one that they emphasize the most as you're going through at least junior high mathematics. But this is another option. All 3 of those work. Okay, any of those are fine. Any questions so far? Okay. Polynomials and rationals. Well, polynomials, if you'll remember, are things like quadratics. X squared plus 2x plus 3. They're cubics. X to the 5th or x to the 3rd plus 5x plus 7. But they can have powers of 7 and powers of 10. They just have to have positive exponent powers. Those are polynomials. This first one tells you that the polynomials do the same thing. They simply allow you to plug the value in. And in fact, these over here, I'll flip back, I promise, numbers 1 and number 2 were polynomials. All right, I have an x squared on the first one. I have linear pieces on the top and the bottom. So the individual top and the individual bottom are polynomials on number 2. So this is a polynomial property that works out really well. And it works for rational functions. That's the example 2 that I had, right? It's actually in rational form. It's got a quotient, so we've got the numerator and the denominator. And it also says I can simply evaluate on the top and I can evaluate on the bottom. And it works just like I would expect it to work. There's a condition on rationals, though. The condition, of course, is that the denominator can't be 0. Division by 0 is undefined. Okay, I've been trying to sort of explain more of that in my household lately because my children are working with rational functions right now in their math class. So remember, one of the reasons the why is it's not just because I said so. It's not a good reason anyway, right? But the reason that it's undefined for division by 0 is you can't turn anything into groups of size 0, right? If I have 15 of you guys and I want you to put you in groups of size 0, that doesn't make sense, right? Where are you going to go? If every group has nobody in it, I still have a whole bunch of people that need to be put in a group. It doesn't work. Or you could say that you can't split it into 0 groups. There's at least one group of us, right? I can't make 0 numbers of groups and still have everybody in a group. Okay, so that's why 0 doesn't work. Let's see, a couple of you are still writing, so let me pause. Okay, so what I want to be able to do, and what I'm told that I can do at least when it works, is simply replace x with whatever the limit is that x is approaching, right? X approaches c, I just put c in for x when it works. So if we take a look at the next one, we're actually going to see that it's not going to work. Oh, I missed one more. Okay, sorry, I forgot this one was here. We'll need it in a minute too, so let's mention it now as well. Theorem 1.4. Radicals. They do the same thing. That's the long and short of it right there. If you have the nth root, remember that means like square root, cube root, that kind of stuff. As x approaches c, we can replace the x with the c. This description here at the bottom where it talks about for all c where n is odd, it's valid for c greater than 0 when n is even. This business right here, if you remember, square roots have to be positive underneath them. Okay, now depending on what math you've sort of seen and thought through recently, you might be like, well, wait a minute, aren't there imaginary numbers? And of course, yes, there are. But we're doing calculus in the real number system. So we're not working with imaginary numbers in Calc 1 through Calc 4, actually. Calculus, as we're doing it, is within the real number system, okay? So we are going to only have values underneath the radical if it's a square root or a fourth root, right? An even root that are positive numbers. And that's what it's talking about there. It says if n is even, so if we have a square root or a fourth root, that's not a good 4, let's try again. Or a sixth root, even roots, I can only have positive numbers underneath there, okay? Otherwise, it's not in the domain. If it's odd, if you had cube roots and fifth roots and things like that for odd ones, you can take a cube root of a negative number. For example, the cube root of negative 8 is negative 2. You multiply negative 2 together 3 times, you get negative 8. So there's nothing wrong with an odd radical having, an odd index radical having a negative underneath it, but the even ones don't work. That's all that's saying at the end. Okay, so this is where I was trying to head to. Oh my word, there's one more. I should probably be looking at my notes as I'm talking. Composite functions, dear heavens. Okay, so composite functions. We've been working with these for quite some time. They show up again in an Algebra 2 course usually. F and G are functions such that the limit as x approaches c of g of x is L. So you've got a function limit. And the limit as x approaches L of f of x is f of L. Notice it changed from C to L. The reason that happened is because they embedded one inside of the other. So the g of x got put into the f of x function, which actually puts its limit into the f of x function, and its limit comes out as L, so this is f of L. Composite functions, we really never have to think about them as they work because, again, they always work behind the scenes. So I'll mention to you when there is a composite function and what's happening, but they work really nicely. So actually I can show you one that we already did. So if we go back to example 2 over here, example number 2 is a composite function. We have 2 pieces that are inside of a division sign, right? We have a piece on top and we have a piece on bottom. And the top can be evaluated separately than the bottom, and then all of that can be evaluated together. That's a composite style function. Not the most intuitive one, but there is one there. Number 1 is also a composite style function. You could interpret that this piece is g of x, that's the way it was described on the previous slide, and then it's input into the f of x, which includes the plus 1. So it's just combining pieces together that are already in polynomial form or radical form or rational form, and so we get to use it almost like for free. There are my examples. They're finally showing up. Okay, so all of this intuitive stuff I keep talking about is going to fall apart a little bit right here. If you try to put in 3 in for x into question number 3, what is going to happen? Yeah, you're going to get 0 over 0. It's in fact really important to recognize that you get 0 on the top and bottom. Okay? All right. Whenever that happens and you get 0 on the top and the bottom, what it means is that we're going to factor what we had to start with, and something will cancel out. Okay? Now, here's the good news. This is not factoring from algebra where things are really complicated and messy and we try to throw all the possible things that can come at you. That isn't what happens. The factoring is going to be pretty clean and pretty straightforward. That said, if factoring is something you've struggled with, it might be something that's going to cause you a little bit of difficulty just because it's come back up again. Okay? So we're going to factor this one. The denominator, so this is obviously a problem. The denominator is the piece that factors, in particular because it's the piece that's squared. The numerator is linear, and 3 and x don't have anything in common, so I can't pull out a common factor. Do you remember how x squared minus 9 factors? Yeah, echoing in 2 places. That's good. Do you remember what it's called? Difference of squares. Very good. Okay. Now, looking from top to bottom, something's going to cancel, but they aren't perfect matches. The 3 minus x on top is most closely related to the x minus 3 on bottom. Agreed? Yes. But how are they different?
Well, it's minus, so we can. It's 3 minus x and x minus 3.
Right? So what would happen if I put a number in? Let's say I put in 7. If I put in 7 to 3 minus x, so 3 minus 7, or I did 7 minus 3, what's going to happen with the outputs? One's going to be positive, one's going to be negative. They're going to be the same number, right? But they're going to be the opposite signs. Agreed? So when I cancel these, which I'm going to do, I'm going to cancel them out. I'm going to be left with a negative because they're exactly opposite signs of one another. Okay? So now I have the limit as x approaches, I left it off, what was it, 3, right? X approaches 3. And I now have negative 1 over x plus 3. What happens if I try to plug a 3 in now? You get negative 1 over 6. Okay, I want to draw your attention to something I did that didn't really make mention of. This first problem I was given, the first step I did, and the second step I did, all have that limit notation. Do you see it? But then, over here, at this point, it's gone. Okay, that's not just I forgot it. There's a reason with what I did. Until I've actually plugged the limit in, like put the 3 in for the x, that notation needs to stay. It's kind of like when you were doing algebra and your teacher said, show your work. And if you missed pieces of the work, but then you put them back in at the bottom, if your teacher's checking your work and not just checking the final answer, they probably fussed a little bit and said every step was not equal to the next step. And I'm going to fuss a little bit, and I'm going to do the same thing, and you'll miss points. Because the point is that if you put an equal sign between something, or you put lines of work, you mean that one step is equal to the next. And in order for them to be equal, that limit that hasn't been plugged in yet has to be there. Okay? Now, it won't always happen that at the end you end up getting -1/6, right? And I don't mean that specific number, but you won't necessarily always get a concrete number even. Some other things have a possibility of happening too, but a lot of the ones we work with, you're going to be able to put the number in at the end and you're going to be good to go, at least in section 1-3. Okay, let's look at problem number 4. Okay, just because we see that factoring might be an option doesn't mean you should start there. You really should start and make sure you really need to do it, because sometimes you don't. I mean, you're going to on this one, but I'm just saying, okay? So we should always attempt to evaluate at the value we're given. So this is 4. So 4 squared minus 5 times 4 plus 4 over 4 squared minus 2 times 4 minus 8. Because if, in fact, I don't get 0/0, then I will be done after one step, right? Whether it factors or not. Okay, so if I evaluate this at 4, what do I get?
0/0.
Yep, we do. And the fact that it's 0/0 puts me back in the same position as number 3. Let me make a comment, maybe a connection that you hadn't sort of thought about just yet. The 0/0, and I ended up getting a -1/6 on the first one. If you were to look at this as a equation, it wouldn't look like there's any problem on your graph at x equals 3. There's an open hole in your graph. Do you guys remember holes in graphs? Yeah? That's what's happening here when you cancel things out like this. So you can get as close as you possibly want to that point, but you can never equal it because there's a hole in the graph. And your calculator can't even show you the hole because it's so small. In fact, it has no dimension at all, right? It has no space or no width or no thickness. So you can't see it on the graph. All right, the hole that is. All right, let's take a look at number 4. So because I get 0/0, it means it will factor. And it will reduce. Whether I still be able to plug in the 4 or not is another question, but it will factor and reduce. So let's start with the top. How does x squared minus 5x plus 4 factor? X minus 1 and x minus 4. Okay? If you're struggling with remembering how to do the factoring, come see me. You're going to have to do some factoring. Denominator. Yeah. There's something that is maybe an awareness for what you're doing here. Remember, something has to match. And the piece that has to match is going to have to be the x minus 4. So once I got x minus 4 on top, I have to have an x minus 4 on bottom, because when I put the 4 in here, that's the part that's creating the 0. Do y'all see that? So I'm going to get, this is telling me I'm going to get an x minus 4 on top and bottom. This piece actually tells me I'm going to get an x minus 3 or 3 minus x, but I'm going to get something of that variety on top and bottom. So you get a little bit of the factoring almost like for free given to you just by the setup of the problem and the fact that when you evaluated it, you got the 0/0. All right, so just like you said, x minus 4 and x minus 4, those cancel. So again, I'm going to put equals, I'm going to put limit, and I'm going to simplify my expression. X approaches 4. I have x minus 1 on top, and I have x plus 2 on bottom. At this point, I do not need to write limit anymore because I'm going to actually take the 4 and replace the x. So I have 4 minus 1 over 4 plus 2, which gives me what? 3/6, and it reduces to 1/2. Okay, this is a really good place for us to stop because if you take a look at the next one, it's quite different. And it has radicals, and we'll pick up there on Monday, all right?